Hello, everybody, and this is the notes on the ideal gas law. This is I guess, the fifth of our gas laws that we're going to go over, and this is primarily for our sophomores that were gone for the California High School exit exam. So, Part H, ideal gas law. Now, you guys got the comfort that you can pause this video, so I'm going to go a little faster than I did this in class. First off, an ideal gas. Zoom out here. An ideal gas follows all gas laws under all pressure and temperature conditions. I'll remind you what that means in a moment. So if you need to, you can pause this and write that down, and I'll explain what that meant. So the first notes we went over, we said the properties of gases are that they're compressible, that you can squeeze them together. They tend to want to be, they have very low densities. They'll fill the container completely and uniformly, whatever they're put in, which means they want to be as far apart from each other as they can. They're surrounded by electrons, the atoms that make them up, and electrons have negative charges, and they want to be far apart. They will exert equal pressure on all sides of containers. So this is just the properties of gases. I mean, you get a good idea for this when you blow up a balloon. The balloons tend to be, they're trying the best they can to get a spherical shape because that distributes pressure everywhere. And then we talked about the kinetic theory. Gas particles, they tend to be far apart when they're moving constantly, as all matter is. But gases they're physically moving very quickly. They go in straight lines until they hit something. They have no attraction for each other because, again, they're surrounded by, if this is one gas molecule over here, okay, they're surrounded by, the electron shells. Well, these are negative charges I'm drawing. If you have another molecule, let's say this is hydrogen gas, okay, well, they're surrounded by their negative electrons. These electrons want to repel each other. So there is no attraction. They want to get it far apart. And if you heat these guys up, if you add energy, they will move faster and farther in a given time. So that's what we mean by, coming over here, that ideal gases, if there was such a thing as an ideal gas, it would follow all those laws under all pressure and temperature conditions. Okay, so this is a theoretical idea. But there are no ideal gases. There's what we call real gases. Okay, real gases do not follow the laws that we just mentioned at low temperature or at high pressures. So if you need to, pause it for a moment, get this written down, and I'll explain what we're talking about. In class today, I was going over, we talked about that if you can cool, if you can take away kinetic energy, heat from an atom, gases, they're going to start to slow down because that's the more energy atoms have, the slower they go. So if you drop the temperature of a gas, the particles go from being far apart. Well, maybe let me make these dots. The particles go from being far apart to they end up because they get very close. And in theory, if you take enough heat out of them, you could get it to the point where there is no spaces between the atoms, which would basically mean they're like a solid or a liquid. They have zero volume. So gases will not follow the ideal gas law when we get super duper cold because the particles slow down so much they start acting like solids or liquids. On the other idea here, at high pressures, if you have gases spread out, if you get these gases and squeeze them together so that you're just physically squeezing them together. Now, we're not taking necessarily energy away from them here. We're just like in a piston, like in those little syringes we're using. You squeeze them super small, they start interacting with each other and doing weird stuff. So highlight this, circle this. This is where gases do not follow the idea of the ideal gas. When they get super cold, or if you get super high pressure. Just imagine if you get super duper cold, you're not moving very much. You're like, oh man, I'm cold. Over here, high pressures. If you get a bunch of people squeezing in around you, you can't move. You don't ideal. So anyway, moving on. Here is the equation for the ideal gas law. It is PV equals nRT. I'll pause this, but please make this lowercase because we don't want to do capital N to get it confused possibly with nitrogen. So go ahead and get that written down, then you can continue here when you're done writing those down. So coming back now, Remember that you have to use, this has to be Kelvin, because all temperatures have to be Kelvin. These are pretty standard now. Oh, now here's a new one. Okay, N is going to be our symbol for moles from our previous unit. R is a conversion factor. Okay, math has the really cool conversion factor pi that relates the radius of a circle to its circumference. Okay, so it's just it's a conversion factor, and that's what R is for gases. And R, the value, the most commonly used value for it is this one, 0.0821. Now the units are liter atmospheres over mole Kelvin. So those are the units. I'll explain that in just a moment. But if you need to, go ahead and pause this so I can show that to you. All right, so figuring at this point you've got this written down. In class, I showed students, and you may have been gone the day, this was a plot that was made in the formation of Charles' law, and what happens is if you have 3 liters of a gas that's at 900 degrees, if you cool it to 700 degrees, the volume shrinks. And because we know from Charles' law that volume is directly proportional to temperature. So as we're making the volume smaller, or actually if we want to say if we're making the temperature smaller, the volume gets smaller. And when they plotted these out, when they took 3 liters of this material at this temperature and just started to cool it down, the volumes got smaller and smaller, and they plotted this graph. And incidentally, if you continue this graph to the point where there is 0 volume, that temperature they formulated, they thought that would be absolute 0 or 0 Kelvin. But that's kind of how they got this. They took actual data and said if you continue this graph to cross the temperature at which you have 0 volume would be where matter freezes. Now, the R in PV equals nRT is kind of like, it's sort of in a way, it's like a, it's kind of like taking the slope of this graph. That's really not quite entirely accurate, but it's kind of a good concept for you. Because in math, they'll give you this and say, what's the slope? So that's kind of what this is. Now over here, we're going to rearrange this equation to solve for R. And in class, I had everybody do this. R equals, so we got to divide this side by N times T, and then we have to do that. So R is equal to P times V divided by N times T. Now we're going to go through and substitute. Standard pressure is 1 atmosphere. That is what we say standard pressure is. Standard volume, I want you to go back to our mole unit. When we were converting to moles, from moles to liters of a gas, well, how many liters was there? And hopefully you remembered it was 22.4 liters, but there was a rule with that. It was 22.4 liters of gas if you had 1 mole of gas, so per 1 mole of gas. So I'm just setting that up, and that kind of works out too, because look at, there's the N there. And standard temperature is 0 degrees Celsius, but we need to use Kelvin, which changes it into 273 Kelvin. So what you end up seeing here, we have liters atmosphere, just like we had over there, and then we have mole Kelvin there. And when you divide 22.4 by 273, you get this. So that's how that conversion factor happened. It lets us interconvert between these, just like the idea of the mole let us convert between grams, liters of gas, and molecules. So you'll want to remember this. So here's a practice problem for you. Now don't go writing this all out, because when we read the problem it says how many moles? Moles, the symbol is N. So we're just going to say N equals, when we rearrange this equation to get N by itself, we need to divide both sides by RT. So number of moles will equal P times V divided by, N over N times T. Okay, so there we go. So this, oh wait a minute, my mistake, we're solving for N. Duh, I know, this is R divided by RT. Please excuse me. Okay, PV divided by RT equals N. That's what we're looking for. Now, just substitute in, because we know what we're looking for. We know how to get it. So this is what we're trying to find. This is how we're going to solve it. So let's do it. Now let's just put in the given. We had 0.813 atmospheres, ATM. We're going to multiply that by the volume, 215 milliliters. Now, whenever you use the ideal gas law, you need to use liters. So we're going to convert that to liters in a moment, but we'll come back to that. We're going to divide this by R. Now, when I divide by R, I like to scoot it. I'm going to do it off to the side. So R is 0.0821. This is just from our notes there. Liter time atmosphere. Now, in math, when you have R down here in the denominator and you're going to divide it by mole Kelvin, okay, just like what we said the units were. When you have the bottom of a fraction and the bottom of the fraction, it flips it up here. So the mole Kelvin will actually end up on top of this, mole times Kelvin. That's just kind of the way it works with mathematics. Just like if we were dividing by half, it's, in essence, you're multiplying by 2. But anyway, so here's this. We got, for every 0.0821 liter atmospheres, there's 1 mole and the 1 Kelvin there. So, and then we got to divide by temperature. We got to do 30 plus 273. And I think everybody in class today said that was 303. Let's see, 7 was 0, and then yeah, so 303 Kelvin. Now, when you set this up, we can cancel atmosphere with atmosphere. We can cancel Kelvin with Kelvin. The problem is we can't get rid of it. We can't cross off milliliters and liters. So 215 milliliters, we want to convert that into liters, so we need to multiply it by a conversion factor. And when we're multiplied by this conversion factors, we want milliliters on the bottom and we want liters on the top. And there are the prefix milli means 1,000th, so that means there's 1,000 milliliters in 1 liter. And that'll let us cancel these. And when you divide 215 by 1,000, it becomes 0.215 liters. So this number up here in our problem, 0.215, you can just erase this if you did it in pencil, liters. Now our liters in our units for R will cancel, and the world is good. And I think when we did this one, we ended up getting, let's see here. Oh, now here's a good rule too. You just kind of practice. I think we ended up with 0.07. 0.007. Let's see. Let's turn this on. So 0.813. We're multiplying it by 0.215. 0.215. Now we've got to divide it by 303. But now with these scientific calculators, we need to hit divide. Don't hit multiply. Unless you're going to put brackets around this, then you could just do times the 0.0821. But with most scientific calculators, we're going to hit divide again and put 0.0821. And that'll equal, oh, I did it wrong. Oh, that's not the right answer. 0.813. Now you're watching me. 0.0813 times 0.215 divided by 303 divided by 0.0821 equals, there we go, there's the number we've been getting all day. Now, when you do this, let me see, that's what it equals, 0.007, and we were looking for moles. Now, if you got 0.004, you were messing up here. You need to make sure in your calculator, if you're doing that, you'll need to put an extra set of brackets around this so that your calculator knows that these two you're multiplying and then you had it up divided. But for regular calculators, this number times this number divided by this number, hit divide again, this number, and you'll get 0.007. So with that, your homework is to do the ideal gas law problems. Now I want you right away, for now, just X off number 5 and 6. Those are dealing with density, and you know what? That's just too much for you now, especially being gone a couple of days. And number 10, we're not going to do that, and we'll do that in class later on. So your problem will be to work on these. And this one is how many moles, so you're looking for N, and that's going to be set up just like you did here in our notes. So you can just look at that and substitute that. Over here, we're looking for volume. And when we rearrange the equation, volume will equal nRT divided by P. And then you just substitute in. Now you're going to have to be careful because on this problem, you are going to have to convert torr into atmospheres because the units for R is atmospheres. So make sure you convert torr into atmospheres before you plug that into the equation. Obviously, you're adding 273 to this one, and there you go. And we'll see you Friday. Stopping.